Okay, so yesterday we talked about multiplying powers with the same base. We broke out scenarios like this, 5 to the 8th times 5 to the 5th. We actually have 5 to the 5th times 5 to the 8th is really the same thing as 5 times itself 13 times. So that rule that we talked about was adding the exponents if we had the same power. We try not to focus on the rule because when you start to learn multiple properties, it gets a little overwhelming. We focus on breaking it out because you're identifying what's actually happening. In this scenario, x to the 6th times x squared is actually x to the 8th. So our rule here, which again, we try not to focus so much on the rule because when you break it out, you can actually see what you're multiplying. You can also use this breakout method when we're dividing. These are the most common types of simplifying expressions you would see. Most of the ones would have like a bunch of multiplication in numerator and a bunch of multiplication in denominator, but then ultimately it's a division problem to simplify. So we can also use the idea behind exponents and what we know it means to simplify if we're dividing powers that have the same base. Okay, so we have 4 to the 12th over 4 to the 5th. How can we break out 4 to the 12th?
4 times 4, 12 times.
So 4 times itself 12 times. And how can we break out 4 to the 5th? Yeah, 4 times 4 times 4 times 4 times 4. 4 times itself 5 times. So it looks something like that. And now you may start to see some patterns. Do you notice anything within that expanded fraction? Because that is still a fraction, right? Can you see anything that can be simplified? Because that's our goal. We're not solving, we're not calculating, we're just simplifying. Is there anything that can be simplified in that fraction? Anything you know about fractions and how you're able to like simplify or reduce them that could come into play here? What do you see? Numbers, yes, we see numbers. What about them?
Isn't it like how many times?
What do we think? If you're looking at the visual on the board, the visual kind of shows you some information, but it's all right now. It's just broken out. 4 times itself 12 times, all over 4 times itself 5 times. What do you think?
Can you reduce the numbers like you would normally do?
So explain that a little bit. Max is saying, can't you reduce the number like you normally would? What numbers is he talking about? It's hard if you just say 4, because that's all we see here. But let's clarify, what can you reduce? What do you mean 12? We can simplify something, but now don't think about exponents right now. Just think about fractions and simplifying them. Is there any way that any of these numbers can be reduced?
Can't you like when you divide, like say for example 5x, you divide it by x, you take away the x. Like,
Why do you do that? Well, you can use this, whatever's up here, you can use as an example.
it's like, can't you like cross out 5 from the bottom, like cross out 5 from the top?
5 what? Break down even simpler, because I know what you're saying. You're jumping to like the big. Start small.
Like 5, 4 is like on the bottom.
Let's start with just 1, 4. Explain what you're thinking with just 1, 4.
Oh, 1, 4 from the bottom and the top.
So Gustavo's saying we should just remove 1, 4 from the bottom and 1, 4 from the top. Can I do that? So Jaden says cancel them out. That's a really common term that we hear. But are we just like getting rid of them?
No.
What do we know about any number divided by itself? It's 1. So this really is just a big 1. And that one is just a big 1. And that one is just a big 1. And that one is just a big 1. And that one's just a big 1. So the layout, the way we laid it out, you can see that you're no longer dealing with 4 divided by 4 because 4 divided by 4 is just a big 1. You can simplify or reduce. Like if you saw, if I gave you a problem and it was like 5/5 x plus 1. Like, are you going to deal with 5/5 x, or are you like, well, 5/5 is just a whole, so it's just x. It's just 1 x. That's the concept here. Right? So if we divide, and it's a non-zero number, like you can't do 0 divided by 0. Any other number divided by itself, you're good. But now look at how this is simplified. 1 times 1. These are my big ones. 1 times 1 times 1 times 1 times 1, which anything times 1 is just itself. So the idea of canceling out kind of comes back into play here because you don't need to really represent just 1 times 1 times 1 times 1. What are you left with? 7 fours, which means I'm multiplying 4 by itself 7 times. So what we just figured out is that 4 to the 12th divided by 4 to the 5th is 4 to the 7th. So what's the relationship? Now yesterday when we talked about if we had the same base and we multiplied, we added the exponents. What do you think is going on here?
You have two numbers with the same base
Same
and
base.
different exponents. And you got a smaller number than the bigger number. So
Okay.
this must be the rule of division where you're subtracting the exponents.
So the division rule of exponents is really just like the opposite of the multiplication rule of exponents. If you have the same base, you can subtract the numerator exponent by the denominator exponent. And I'm very specific when I say that it's the numerator exponent divided by, or subtracted by, the denominator exponent. So in this scenario, and we saw it, we broke out the 12 fours, we broke out the 5 fours, we identified our big ones, and we were left with a big fraction that just had 4 to the 7th in the numerator and 1 in the denominator. I don't need to show the 1, so I'm done. Go ahead.
I was gonna say maybe you can think about this in inverse operations, because like the inverse of multiplication would be division, meaning that you would do the opposite.
Yep, if you're just dealing with the rule, it's really just the opposite of what we did yesterday. Again, we try not to focus on the rule because there are multiple properties of exponents that we're going to be learning in the next week and a half, and the rules can get a little overwhelming. Notice that our process to figure out how to simplify is the same process as yesterday. If you break everything out, you're still going to see what you need to reduce. So make sure you have this written, and we're not drawing. The division rule of exponents, if you have the same base, you're subtracting the numerator's exponent by the denominator's exponent. So in this scenario, if you did have that problem and you just use the rule, 12 minus 5 is 7. And there's other examples which we're going to look at in just a minute. But really, you're eliminating your big ones. We'll do another example. If you need to show the breakout of 4 to the 12th over 4 to the 5th, it's a good example to have. Show your big ones, you're left with 4 to the 7th. That's a good example. So let's go through this example. At this point, we're kind of doing a similar problem to simplify. The only difference is now we have a couple of coefficients. How would I break out 15x to the 6th?
15 times
And that's all over. Notice I'm still using the fraction bar so that I can clearly see what's in my numerator, what's in my denominator. What's in my denominator if I break it out?
3 times x times x times x.
Okay, what can I simplify? Go ahead.
You can divide the 15 by 3.
I can work with that coefficient. 15 over 3, or 15 divided by 3 is what? 5. Good. So I've simplified that. And now what? What else do I have?
You can like we did with the other
What do you see here?
axis.
Okay. So use different terminology. We don't want to just say cancel them out. What are we reducing? So this is a big one, and a big one. That's just one hole. I know I say a big one, but it's just one hole, and one hole. So we can eliminate that. And you're not really canceling it out because it's there. It's just a 1. And then what are we left with?
3.
X to the 3rd. So I used it, I'm simplifying. Now there's a few other types here that you may see. And these examples, they've been like nicely laid out, but you may have an example like x, I don't like that spot on the board, x times y times y times y, all over y times z, right? So in this scenario, they're not perfectly lined up, but they still do reduce as a whole. Y divided by y is a whole, and then y divided by y is a whole. So I'm left with x squared y over z. Notice I can't just like move the z, it is still in the denominator.
What happens if you have less on the top?
Good question. And that's actually where we're going next here. Let's say you have less on the top. Give me an example.
4.
Let's just switch these. How about we do that? Let's just switch them. 3x to the 3rd. Actually, we'll leave it as a 15. So we'll say 15x to the 3rd over 3x to the 6th. Let's use that as an example. Okay? We're still going to break it out. We have, how do I break it out on the top? On the numerator?
15
15 times x times x times x. And how about the denominator?
3
times
x
Okay. Where are our big ones? Or our holes? I keep saying big ones. Where are our holes?
We can do 15 divided by 3.
Because we can do 15 divided by 3 is 5. So that we've eliminated. We've reduced. Okay. Now, this is a big one. This is a big one. And that's 1. So what am I left with?
3.
X cubed
Where is it?
in the denominator.
It's in the denominator. Okay, you can't move it. Like I did a lot of students in the first class, we didn't specifically go over this. It was one of like the challenge problems that they had to figure out. And a lot of students would have said that. But it's not x to the 3rd. It's 1 over x to the 3rd. There's actually an x to the 3rd in the denominator. We're going to talk next week about negative exponents, because that is a negative exponent, which you'll learn next week. But that's why, if you notice, when we go back here to this rule, I was really specific when I gave you that rule and said it's the numerator exponent minus the denominator exponent. So if you just had x to the 3rd over x to the 6th and you followed just the rule, you would have x, 3 minus 6 is negative 3. We're going to go into what a negative exponent is next week. And then we're going to put it all together. Okay. So we're going to do some practice problems. It's actually part of the Galactic Hero assignment you were working on yesterday, but the one that we actually would do for this topic. Because that assignment, it's 4 pages. Each page is a different topic. The first page of that assignment in Galactic Hero is multiplying. The second page is dividing. The third page is raising a power to another power, which we're going to do tomorrow. And then the last page is like 0 exponents and negative exponents, which we're going to do next week. So here are the ones that we're going to focus on. Which ones did we do? So your one, actually, no. 1, 2, 3, 4,
Wait for you.
6, 7, 9. Actually, don't do that one. 6, 9, 12. So I want you to try these 7, and those are going to be your most, I don't want to say straightforward because that's not really the word, but these are similar to the ones that we've done. Okay. Number 10, 11, 13, and 14 are, whoops, not what I meant to do, are going to be your more advanced. Okay. And they're not necessarily harder or easier, they're just a little bit more complex. So we'll start with those 7. And again, this is a Galactero assignment. So assuming after your DOL, you'll go back to finish it. Some of you finished yesterday and got 2,000 points right away. Boom. And that assignment, it's 2,000 for each page. So that's going to be an 8,000 point assignment. So we'll start with this. The first 7 in red are going to be your most similar to what we just did. And then the 4 that are in blue, it's the same process. You would just have to break out more. So let's say 15 minutes. 15 minutes. I am going to need to stop the recording for just a second. So this is going to go away.